There have been many landers and rovers sent to the moon, and some have survived for a little while, but most will come to a short end. And that is because the moon is both incredibly warm and incredibly cold. And you get this long day-night cycle where it's 14 days of sunlight and then 14 days of cold. And it's very difficult to make a spacecraft that can survive those two temperature regimes. When it's hot out, no problem. You just got to have good radiators and lots of solar panels, plenty of power. But when the night comes in, then you are giving away all of that heat, and very few battery systems can keep you warm enough for 14 straight days. So my guest today has been awarded a NIAC contract to try and solve this problem. Today I'm talking with Dr. Austin Phoenix. He's a research associate professor at Virginia Tech, and he and his team have been awarded a NASA NIAC grant for ECLIPSE, which is the Efficient Variable Conductivity Lunar Insulator for Passive Surveyor Environmental Control. And this is a smart insulation system for lunar rovers, and I guess other locations as well, where you change the way the rover sheds heat depending on whether you're in the daytime and you really need to get rid of the heat quickly, or whether it's nighttime and you need to hold on to your heat as long as you can to get through that lunar night, and that you need to be able to switch between those two temperature regimes. So if you are interested in solutions to why do rovers die on the moon, I think you'll enjoy this conversation. Austin, I'm pretty excited about this interview because you are going to be able to scratch one of the why don't they just comments that I am always getting from my audience when we talk about the big problem with the moon, that you've got this really long day-night cycle on the moon that is just brutal on spacecraft engineering. And you have been awarded an NASA NIAC grant to try and tackle this problem. So first, let's set the problem. Why is the moon such an awful environment for deploying a rover?
Yeah, really great question. So, when we think about most electronics, they work really well in the Earth environment, right? You have that air to help cool them. Thermal mitigation is a huge challenge when you start entering space in general. And we spend a lot of time and energy working on the thermal challenge for satellites. But what's much harder about the lunar environment is that longer day-night cycle. And when you think about, the conventional moon landings, we, kind of timed those to certain parts of the lunar day to help prevent these kind of enormous shifts. And so the lunar day is, of course, much longer, and that introduces this both, kind of fairly high temperature environment during lunar day that you have to both operate in. And in that future lunar economy, the hope is that we have distributed rovers, mining operations, transport systems that are out there on the moon. And so, as we look at that problem, both you have to have a system that can reject that energy you're generating. Electronics are pretty inefficient. They're pretty efficient, but they generate a lot of heat, and you have to release that heat. And then once night hits, all of a sudden you're in a really tough environment, both because most of these small scale systems are going to leverage that sun for a power source. And so not only do you need to heat yourself, but you also lost your primary power source.
I've reported on many of these spacecraft that have landed successfully on the moon or crashed pretty hard, but have continued to operate during that lunar day. And then the lunar night kicks in and the temperature, like it switches, like you're at 150 plus Celsius on the day, and then you're negative the same on the night. It's a huge swing. And always the question is, will it come back? Will it come back? Will it, after 14 days of being in this bone-chilling darkness, which is death to batteries, really hard on electronics, will it be able to restart? And occasionally they do, but mostly they don't. That they're all operating time is just this 14 days of sunlight, and then that's it for the spacecraft. And that's a tragedy when you think about the expense to build the rocket, launch the spacecraft, get it to the moon, have it do quick 14 days of work at maximum, and then that's it. It's disposable, it's thrown in the trash, and then you hope to launch a new one. So that environment is awful. So what are the methods, the strategies to try and mitigate this that have been proposed in the past or even used today?
Yeah, you make a really good point. It's not just that it gets very cold, because we can manage that, but that it also gets pretty darn hot too.
Yeah.
And so there are a couple ways, especially as you look at small systems, that you can make them survive longer than that kind of one lunar day cycle. And one is you bring your own heat source. There are a lot of these for these longer term missions that you have a radioactive, often, source that you're just leveraging to heat your electronics, heat your batteries, so that that environment looks a little bit more like Earth. Not quite, but makes it a little easier to manage the thermal swings. And that at least prevents that, getting too cold, but it does introduce a bunch of weight. There's some dangerous aspects of these kind of heater systems. And you also, if the system fails or your thermal management system fails, you could easily overheat your electronics as well and die in that way. So it introduces additional failure modes. So it's unique about the proposal that we have with NASA on the NIAC is really that we're trying to simplify the problem in multiple ways and develop a more dynamic thermal control system that can passively manage that hot thermal environment and the cold thermal environment. So their previous technologies, thermal switches are one of them, where it's basically a block of metal, and they introduce an air gap in that block of metal. When that air gap exists, very little thermal energy passes across because it's in vacuum, and you're really relying on a radiative heat transfer. But as that system warms, that air gap actually closes, and you have a conductive thermal path, which is orders of magnitude more effective at conveying energy out of the system. These are commonly used on rovers, on kind of these, complex systems. And that gives you two thermal conductivity states, which are really useful to enable basically you to have a box of electronics, for example, that is heavily insulated except through this thermal switch. And if it starts getting warm, starts heating itself up through operation, that thermal switch will close and it can start dumping energy to its environment, often through a radiator, where the innovation that we're generating is that we're going to look into miniaturizing that thermal switch and effectively leverage what is unfortunately an overused term, a metamaterial, and in this case, a variable thermal conductivity metamaterial. So what we're going to do is architect and design a material that's bulk properties have an arbitrary thermal conductivity as a function of temperature. And at the cold case, we have air gaps within that system. And we're, unlike the thermal switch, going to use multiple air gaps because by stacking them, that decreases the minimum thermal conductivity of the system because, you basically have to radiate through multiple layers, which gives you a much lower effective thermal conductivity. And then we're also going to design the shapes of those plates so that as we apply a load to that system, we can control how those new thermal contact pathways are developed and are generated through that temperature swing, so that we can introduce other stable regions between these two high conductivity states and low conductivity states. And what that enables is we can really make a system a passive thermal control mechanism. And so if I want to operate between 20 and 40 C, if I can build a thermal metamaterial and I can connect that metamaterial to my electronics, to my hot object that I want to cool on one side, and on the other side I can put my cold object, like a classic spacecraft radiator or some mechanism to cool that system out into space that is also passive, right? Then what I can do is as that system heats up beyond that 60 C level, that metamaterial can close and have a very high conductivity and begin rejecting heat to the environment much more effectively. And then once it's rejected enough heat, it'll cool itself back down and the metamaterial will open to some intermediate state. And then if it, starts to get a little colder, that metamaterial will inherently open back up again, reducing the conductivity even further and basically preventing any of that heat to reject away. And so at the end of the day, that system ends up looking like, at the hot case, when I'm, really running those electronics, I'm driving that rover around, I'm, doing the kinds of things that a future lunar economy is going to need. Then I've got a big radiator. I'm able to reject all that heat really efficiently. I'm able to cool my system down. But during lunar night, the intent is that I can take a very small vehicle that doesn't need either auxiliary power, it doesn't need an auxiliary heat unit, some, you know, um, radiative heating mechanism on there, and can instead have a pretty simple, small system that is able to basically disconnect itself from the radiator, disconnect itself from that thermal environment around it. I can heavily insulate it, and then it can just sit there and use that latent heat to survive lunar night. And the goal of this effort is really to demonstrate that no auxiliary power is needed overnight. So the idea would be right at the end of the day, I kind of go into a shutdown mode. That system kind of shuts all its processes down. It then has some power left in its battery, but we want to leverage that power to do fun things on the moon. We don't want to use it to heat ourselves. And so the hope is that through that entire lunar night, it just sits there cooling slowly, but well above the electronic, kind of death temperature, or at least risk temperature, where you're going to start killing batteries and electronics. Allow it to cool a little bit, but minimize that cooling as much as possible so that I don't even have to turn a heater on and waste any of that preciously earned energy on anything besides driving that rover around and doing exploration and doing the things we want to do.
So if I was to take this rover and cut it in half with a bandsaw,
Yeah.
what would I be seeing then of all the different metamaterial layers that are sort of sandwiching this thing together?
Yeah, really good question. So, as we build these systems, there's kind of you have sensitive components and you have non-sensitive components, right? That are going to really struggle to survive that lunar environment, and things that aren't. And so the idea is, maybe you have an electronics box, you have kind of the brain of the system where you really have those, critical temperature sensitive components. And maybe those are sensors. Maybe they are, different systems rather than just, the memory, the computing, the conventional things that we would see. And so what we would do here is we'd heavily insulate that using, conventional insulating materials around that system so that it is, kind of thermally disconnected from the rover itself as much as possible. And then on one interface, we would place this metamaterial. And the idea is it's fairly thin, it's low size and weight, and no power required. And that thin material is really leveraged as its primary thermal interface with. And so you can have power plugs elsewhere, you can have other systems in there, but from a thermal perspective, everything's fairly well insulated except for that singular interface. And that interface would then connect, probably with some thermal straps, or just have, the conventional thermal design of a thermal pathway from a radiator to that metamaterial. And so that metamaterial is really its thermal interface with the world. And the piece that I'm really excited about is that system could be made active, but through the use of, shape memory alloys and clever design, we can make a thermal metamaterial that's fully passive, that's just responding to the temperature of my rover and operating as I hope for it to. And so, that metamaterial in and of itself, if you did a cross section of that, what you'd see is, two stiff outer plates, which are really our key thermal interfaces to the world, one being on our rover electronics and the other being our thermal path to the radiator. And then in between, we're going to have a mix of, vacuum filled air gaps and some bent, three-dimensionally bent plates in between them. And the intent is that as we squeeze down on that system, either using coefficient of thermal expansion mismatch, in this case, we're focusing on shape memory alloys as the, passive actuation mechanism, though you could attach a conventional actuator to it. We, kind of clamp down on that system, and those plates will then touch. And the moment they touch, we've got a new thermal path in that system. And the way that we bend those plates, the way that we crush on it as a function of temperature, enables us to control those thermal path lengths and cross-sectional area. And as we continue to crush on it, we end up with just, a block of metal that are separated by those interfaces. That's a very high conductivity material. And so the intent is that we can achieve not quite, but fairly close to the maximum conductivity of just a block of copper. within a couple, a factor of maybe, 2 to 3 times worse in total conductivity, but in of maximum conductivity. But on minimum conductivity, we think we can get 5 orders of magnitude lower. And so that gap is what enables us to be really well suited for, I'm doing a bunch of science, I'm driving around the moon, I'm generating a bunch of heat, and I'm getting a bunch of sunlight hitting me and warming me up, surviving that extreme case, as well as I've got no additional power and it's the end of lunar night and I'm about to freeze, but can I just survive that last little bit of energy to keep doing science and make that system a little more effective?
So the size of the rover must come into play where this system would work amazingly well for something that was the size of a building where you've got this nice air gap, you got good insulation. Like my house, we've got really good thick insulation here in Canada. Our power goes out all the time, and the thermal mass of just our floor, the concrete on our floor, will take all day to go down just a couple of degrees Celsius in our place. But if you had something that was really small, then it would run, no matter how much nice insulation you've got in there, it's still going to get out. So is there are you sort of targeting a minimum size of a rover that this system would do the trick for you?
Yeah, it's a really good point. So, how once I'm in that cold state, right? How long I can survive is exactly as you said. It's a function of how much thermal mass I have and how well insulated I am. And so there's that exact trade. Now, because we're very mass constrained, because it's so expensive to get mass onto the moon, right? We're actually looking at trying to solve the problem with a ton of insulation so that we can have a really small thermal mass and really limit how much of that energy gets out of it. But what's unique is that today we have technical solutions to solve this problem if you're very large. So if you're a really large rover, you're thinking, kind of the, Mars scale SUV size systems, you have a lot of power on. And that gives you multiple options to solve the problem. You can just ensure that you've sustained enough power on board to heat yourself as you get cold throughout the night. You can also, in those cases, bring along, for a system like that, you can bring along additional heaters and mass that don't necessarily require power, like, the RTGs for energy generation, or just leveraging inherent, heaters from radioactive decay and other mechanisms. But where there's a fundamental limit is at those smaller sizes, you can no longer either carry enough power to survive that lunar night or carry these auxiliary systems that would enable you to operate it. So we're actually targeting the really small systems as our attempt to enable new capability. And while you're right, it is easier to implement this material on a larger system. It's really the smaller systems that are going to be most benefited.
Well, and that's what I was sort of wondering is how small does this let us get those small, single purpose rovers that are designed to answer some kind of science question, but maybe you want it to last month after month after month on the lunar surface. With Curiosity and Perseverance, they've got this giant chunk of decaying plutonium. The analogy I always use, if you've ever watched The Martian, there's a scene in that where he goes to the RTG that they had for their base, and he pulls it out of where they had left it, because now this is a heater that he can use to keep the rover warm while he's driving around and not have to expend his energy. But even Spirit and Opportunity, they had little pebbles of this plutonium on board that was designed for this job to kind of just provide heat to the batteries so that the batteries didn't have to expend all this electricity to keep itself warm. And so when I think about this, is there a minimum size rover that you figure, okay, I mean, and maybe this is the purpose of the NIAC grant, right? Is like, you're now going to figure out what is that smallest rover that'll do the trick without any auxiliary, like without it including a little piece of plutonium inside to keep it warm. Is there a minimum size where now you're surviving dependably without any auxiliary power, without any auxiliary cooling, month after month after month on the surface of the moon?
Yeah, I mean, one of the challenge is, in the comparison to leveraging a plutonium heat source is that, man, that plutonium gets real hot. It is very mass efficient if what you wanted to do is generate some heat. But I think my vision for that future lunar economy is that we are going to have, some permanent presence on the moon. We're going to be having spacewalkers, astronauts out there operating on the lunar surface. And there's a lot of danger to having plutonium in every independent operating.
Yes.
And so, while we may require a slight addition in, total mass of the system compared to a well integrated, heat source like what they use for the larger systems, the intent is that we can provide secondary benefits as well, both in maintaining the temperature within tighter control bands, preventing thermal stress on those electronics by minimizing the excursion of those temperatures, both in the hot and the cold region. And so there is a point where, as you get incredibly small, that you're right, those kind of sources where you're talking about a couple grams to heat your system may win out. But I think the intent is today, without those auxiliary heat sources, you are fundamentally limited to fairly large systems, because those are the ones that were willing to put these auxiliary heat sources on, or the ones that can heat themselves in other ways. And so we're really looking at, kind of technology sets that are more of the disaggregated, distributed, a third the size of Challenger, smaller, that would be a real enabler for kind of these mining, exploration, kind of missions, and enable you to also be a little more dynamic as you're operating out there, to go into craters and shaded areas of the system and have, a better trade. So I think there is some, work that needs to be done to say, what is that minimum viable, kind of system. I would also say, though, that even, there is kind of this sweet spot of the technology where, I don't think our plan is to, make all of our systems radioactive if we can avoid it. But there is this sweet spot of system in that kind of smaller rover scale that you just don't have enough power to operate independently. And so that this is really focused on an enabling capability for independent systems, so that we don't require that rover who's trying to do an exploration mission coming back to the power source every night, or coming back to the hub with the inherent risk that if it doesn't make it back, it dies, and that those electronics and battery will have to be replaced.
But I'm thinking about CubeSat type things, tiny little rovers, things that are on the order of 10 centimeters, tens of centimeters. Like, there are missions in the works that are proposing ideas, and that's in the fully disposable class right now. And then you have larger things, maybe on the meter scale, or maybe a couple of meters across, for something like Curiosity or Perseverance. And that use case, I mean, just the thermal mass probably gets you surviving through the winter night, the lunar night, as long as you've got enough, batteries on board to kind of handle that. So, am I imagining small CubeSat sized rovers that are deployed on the surface of the moon and still being able to survive the lunar night?
Yeah, I think that's exactly the intent of this technology. So our initial, kind of mission that we looked at before we kind of pivoted to the rover was a CubeSat integration. And so CubeSats have both some nice comparisons out there and some good data. So our initial study really looked at comparing this metamaterial to a 1U active thermal control system that exists on a CubeSat. So when you're thinking about a CubeSat, I've got a 6U CubeSat. Maybe I am willing to allocate one of those 6 U's of volume to thermal management of that system. What we were looking at is, let's replace that 1U CubeSat system, enable that 1U for something else, and replace that with about a 1 centimeter thick by 4 by 4 centimeter cross section metamaterial.
Right. And for people who aren't familiar with the terminology there, the U in a CubeSat they're like a 10 centimeter by 10 centimeter slice. And I forget how thick the slices are, 1 centimeter, 2 centimeters. and then you stack them up. And so you'll have a 6U will be the equivalent of 6 of these together, which is.
So they're kind of these 10 centimeter, cube blocks that get put together to make up. And so that 6U is 6 of those blocks in different orientations.
Right. Yeah.
And so, the kind of state of the art in the active thermal control for satellites is that kind of 10 centimeter by 10 centimeter by 10 centimeter cube to build an active thermal control system into it. And so we were looking at a much smaller volume, 250 times less volume to achieve, but we hope to be the same level of thermal control. And so to date, we've done some nice initial modeling efforts of the metamaterial, looking at how it performs, some initial understanding of how to design the systems, what material choices, what geometries, what active control system do we use. And then we've done some very initial studies where we've placed that metamaterial into a CubeSat, and then we've also inserted it into a rover and evaluated how that system performed through the lunar night and through ECLIPSE and other cases for the CubeSat. And so I really think that kind of scale system, you're talking, less than a meter squared of volume, is really where I think this technology is a true enabler. That without some system like this, you're going to need, and inherently those systems are intended to allow a lot higher level of risk, right? If you have a Challenger style large scale system, that failure rate has to be incredibly low because that's a really valuable asset. You're not going to allow that to go into caves that you're not certain it can come out of. But, kind of that CubeSat vision for a lunar rover is exactly where you get to do more of the fun science and actually scale the amount of volume you're able to take sensor readings over and really distribute those systems out. And so the hope really is, can we enable those systems and thereby enable that future?
Yeah. And I can imagine that there's this really nice sort of separation between chassis and payload where, you're spending, say, $100,000 and you've got the sensor suite, the CPU you've chosen, the RAM, the bus, and that all sits in this nice box. Maybe it is a 6U, and then you've got it's got wheels, it's got, right? And it's got all of the gap and the metamaterial and all that sort of built in. And so you spend your $100,000 to design and build your CubeSat at your university. And then you take one of these off the shelf, lunar ready sort of chassis, and you just slot it in, make sure the insulation is going. And then you can plug it into the next mission that's off to the moon and bundle a whole bunch of them together. It'd be great to sort of see one of these future lunar landers deploying a swarm of landers, of rovers that all have different jobs, right?
Yeah, I love that vision of a kind of a universal small scale rover out there that's able to drive itself around, and you design the payload and the brain in it and go out and tune it for whatever mission you need. Because I think that my personal hope is that we can really, with clear mobility, opens up new things that we can really, really do that we can't easily do today. And so, it's hard to get around the moon. It's risky to get around the moon. It's slow going to navigate these processes autonomously. But part of that is that, the assets that we're using to do that are incredibly valuable, both from a scientific perspective and the cost to get them out there and the amount of R&D work to ensure that they never get caught. But if we're able to build small, cheap systems that are allowed to fail 5% of the time, and that have useful components on them that we could reuse and go pick up at a later date, and as you said, plop in the next science payload that we've developed over the last couple of years, that really would be a cool enabling technology. And I think one of the key, miracles that need to be solved to get out of there is the thermal challenge to enable that system to be a little lightweight, a little easier to build.
Yeah. I mean, right now you could do those, but you just have to know that your rover lander, whatever, has got 14 days at maximum and then it's dead. But in this case, wouldn't it be great if 3 years later, Minor Explorer 17 is still responding every time the sun comes up, and you've now sent it to its 14th rock to look at and examine the characteristics of it. Or, there was a great mission that I really like, or a great idea, where you build an interferometer on the moon, a visual interferometer. And so you have one telescope on the lander, and then you put another telescope on a rover, and then you drive it, say, 100 meters away from the lander, and now you've got two telescopes that are working in concert as an interferometer. You could deploy a bunch of them, and they can fine tune their distance month after month after month to really resolve all of the issues that you might be having. And so just like keep the cost low, have your rover come back to life on every lunar day, totally changes the math of what's possible on the moon. Austin, the question I always ask people, what are you obsessed with right now?
Yeah, that's a really good question. So, where I am really excited and where I've spent my career is in looking at problems where I can take a structural system and leverage its environment to make that system better. So in the thermal metamaterial case, how can we leverage the inherent thermal changes in my system and leverage the mechanisms within the materials that we develop to have it effectively be a smart material and sense its environment and change its behavior based on that environment. So in the metamaterial case, it's how do I use that temperature change as the primary mechanism to minimize, the thermal excursions of a satellite? Or how can I use thermal shifts in my environment to actually intentionally deform and twist my system into orientations that I want to be in? And so as a, structural engineer, as a dynamicist, what I end up doing is working with collaborators in other fields to identify how a shape change can benefit the aerodynamics of a vehicle, or the thermal shift in an environment can change how my structure performs in the system. And so I really am looking at these interdisciplinary edges of multi-physics systems to try and find new things that we can exploit, leverage, and make smarter, more adaptive systems. And one of the things that I think about a lot is, as a mechanical engineer, when we design systems, it's often for outrageously long maintenance and lifetimes of systems. A silly example is, the F-35 was thought up 90 years before its planned obsolescence date. And so as we look at how do we build systems that are going to be operated by multiple generations of engineers after us, how do we build more adaptability and intelligence into these so that they can operate how we want them to operate on day one, but be able to operate how we could never even imagine they will operate in the future?
And so if you bake in some of the performance just into the materials themselves, then that's not a part that necessarily requires maintenance or to be swapped out or whatever. I sort of think about, I don't know whether this exists, but you imagine that you've got a jet turbine or something like that, where when it runs hot, then whatever are the metamaterials in it are configuring themselves for longer sustainable operation at that high temperature, high speed. And then as you slow down and you're coming in for a landing or whatever you're doing, then just the shape of the metal in the engine itself is better equipped for a lower speed environment and a lower temperature environment. And you're not having to kind of have actuators and things that can break that are switching between those two.
I'm really glad I already wrote that proposal, so I don't have to
Perfect.
credit you on it.
Great.
No,
Great.
You didn't quite snipe me, but yeah, we've been talking with NASA. We had a proposal that wasn't yet successful, but looking at how do we make supersonic engines more efficient and able to control the acoustics and the efficiency of subsonic, transition speeds and supersonic speeds. And so these systems that have to operate both low to the ground and slow and quietly are hard to build to also make them fly efficiently when they're subsonic and efficiently when they're supersonic. But that's exactly the idea here, is how do we make this system able to more adaptively respond to its environment? And when you think about, an aircraft and these other systems, they're often, we kind of are in this, set it and forget it mindset, or an altitude or cruise speed is constant, but its mass is changing, right? So how do we build into these systems that are changing where can we find these little bits of additional flexibility, or we don't have to design for, I am, at full of fuel and cruising at this speed on the hottest day of the year, over Arizona. We should fly it a little differently, and the engine should be configured a little differently to be flying at the coldest day of the year without any fuel. And how do we build systems that can, either passively measure their environment and adapt, or for these more complicated systems, have a very intelligent system measuring the external environment and fine-tuning the performance of the vehicle itself in real time.
Yeah, I think about Venus as sort of the worst case scenario of this kind of thing. And there's been some great proposals come through NIAC about, can we just change the way electronics work so that they are happy at the highest temperatures? And maybe they're not going to work at the same level of efficiency as something that's really cold, because, heat is always the problem. But that you can say, well, like, what if you can custom build the equipment for that habitat that it's trying to be in? Maybe there are solutions there. And, there isn't a lot of heat differential or stuff that you can work with in a place like Venus, but still there might be, solutions there.
Yeah, there's some, inherent physics challenges of how do I keep a closed system cold in a hot environment like Venus? And there's no clean answer there. So just how do I make my systems survive hot? And a real piece, an area that we actually just started. We just got funded on an SBIR working with a small company, ORCID, to help them test and evaluate some high temperature electronics systems in higher temp and vibratory environments to kind of start the long pathway that we have to go to being able to have electronics that can just happily operate in at least a Venus temperature. I'm no pathway to a Venus atmosphere necessarily.
Right. Or sulfuric acid rain,
Yeah, that seems, baby steps, right? But
yeah.
That environment is really extreme. And, there are cases on Earth where we could really leverage some higher performance extreme environment systems that don't rely on kind of the thermal control problems that we bring to bear. But I guess I've got job security on the thermal control side because, we're really good at making really awesome silicon electronics, and we're going to be using those for a long time. But I'm also really excited about these new material systems that we can leverage to maybe push the extremes of where we can go, exactly like that Venus solution. But that's crazy.
Yeah, totally. Yeah. That's like where I guess engineering solutions just go to die. It's Venus. Yeah. Austin,
what temperature do you want? Wait, what's the pressure? Wait, okay. What do you want me to
do? Yeah, exactly. Yeah. I'll give you 20 minutes on the surface of Venus. Yeah. Austin, absolutely fascinating work. Thank you so much. Congratulations on your NIAC grant. And I look forward to the final report and then your phase 2. And then the actual rovers on the moon. All right. Take care.
Really appreciate the time.
I hope you enjoyed this conversation with Austin Phoenix. Now, we had a longer conversation about a completely different technology that he is working on with some of his students. And this is, imagine a measuring tape that you put out where it has 2 stable modes. It's wrapped up inside the tape measure, but it's also stable when it is extended because of the shape. What if you put that in space? As always, we put the longer versions of our interviews over on Patreon, but it's completely free. There's no ads. You can just click, go watch it right now. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Dark Finga, David Gilton, and David Matz, and to all our reading and math for toddlers, Evan.pro, James Clark, Jeremy Madden, Jim Burke, Marcel Smith, Michael Purcell, NASA Ocean Guy, Nordspace, OneSeveranimals.org. Please follow my nephew at VBrick6994, Rankaidu, Richard Williams, Sean Sargent, Stephen Filemonley, Team 49, Telescope Scan, Vlad Chaplin, Wolfgang Klotz, and Zelda. Oh my God, we have proof of aliens who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. This is great. I always love when I am able to scratch one of these why don't they just problems. Every time I talk about spacecraft dying on the surface of the moon, people have solutions. And this is a tricky problem. Like, this is a really complicated engineering problem. And the solutions are just put plutonium in your spacecraft. But, that has some issues. Where are you going to get your plutonium from? this stuff is putting out a lot of heat, which is great at night, but not great during the day. Or you make something that is just really big, like just build a bigger rover. But of course, delivering mass to the surface of the moon is just so expensive. And if we can make these tiny little CubeSats, but have them operate on the surface of the moon, that would be a game changer. There are plenty of universities where the students are able to just build CubeSats and then have their mission fly as part of a ride share. And the cost is very low, you know, in the tens of thousands of dollars, not the tens of millions of what it would normally cost. And so there are some interesting options that could be opened up if you could make a spacecraft handle varying thermal environments. So it's a great idea. And this is the kind of thing that NASA NIAC is just, they're going after hard problems, no easy solution, out of the box thinking. Let's see what people can come up with. All right, I hope you enjoyed this one, and we'll see you for the next one.